So I'll just try to introduce my research. So I'll use pull everywhere and just make.
You'll have to speak up though.
I'll use pull everywhere just to hopefully make it fun. You can. You can you scan it if you want to.
We have to do something.
If you want to scan, if you want to participate in the poll. Make this one.
It says I do this in restaurant. He says we.
Keep going.
We're not that fast. Let's see.
And this is one of the things I discovered to be good when I was teaching in 26
So.
Well, because they wouldn't answer my question if I don't do this. But anyway, the motivation is that I have not been successful in introducing my research to non-statisticians because whenever they ask me, what is yours, what do you work on? I would
It's loud.
probably say some jargons and statistics and like causal inference, things like that, and just don't ring a bell to them. And if you want to look, this is one sentence summary on my webpage, which is probably too abstract for you, for non-statisticians. There will be some math, but I will try to keep it simple and interpretable. I will restrict to large, independent, and identically distributed samples like usual ID set control, just to keep things simpler. And you can ask me any question during the talk. And the first thing, Happy Chinese New Year of the horse. There are two horses. This is actually a horse. It's not. Whatever. Okay. So in the pull everywhere, you can put in keywords like t-test, linear regression thing. You can put in things like follow areas. I'm just following whatever other people are doing. It doesn't matter, or you can just say I don't know. And the poll is anonymous and can submit multiple responses if you want. First. So let's say we observe outcomes from two groups, like exposed versus unexposed, like XY, XN, and Y1 YM. How would you analyze the data to compare the mean outcomes of the two groups?
Yes.
Really simple. Nova. Only one answer. Test.
What was the question again?
You got two groups.
Oh, the compare means.
Yeah.
Oh, okay.
Line test.
Yeah, go some ransom tests.
Well, it looks like a lot of LRT ratio test. Okay.
You're going to send more.
Still speak a little louder.
Oh, okay.
It's like a big fan back here, so it makes it hard for us to hear. There's some kind of like, I don't know what it is, but.
Okay. Let me try. Wilcox. Okay. You guys have a lot of answers, but it seems like a lot of people answered ANOVA or t-test. Okay, so if you want to use t-test or ANOVA, what would you do if the data is not normal? Sorry, let me just go to the next one. Okay, my good. Wilcox, I assume you're assuming GLM because there's no clustering. Linear model, large sample test method. The other. So now if you want to use Wilcoxon ransom test or Matt-Whitney test, take a second to think about what the null hypothesis is. Go ahead and answer. I not necessarily put it in because it might be too hard. Okay, just think about it. And here's the answer. The null hypothesis is that with X and Y denoting two independent random variables from the two populations. So you randomly draw one individual from unexposed group, randomly select another one from the exposed group. The probability that X greater than Y equals the probability X less than Y. So is this kind of scary? I mean, is this really what we want to do in terms of comparing the group means? I mean, something to think about. This is just my personal preference. If you want to do a self-driving approach, I mean, if you want to use some off-the-shelf, I would do unequal variance t-test because it's approximately valid in large samples regardless of normality. So in that sense, two sample t-test is already non-parametric in large samples. And I indeed work on non-parametric methods, but not methods like Wilcoxon ransom tests. Okay, let's go to the next example. So suppose we observe exposure X, some covariate Z to be adjusted for, and a continuous outcome Y. How would you analyze data to assess the association between X and Y, adjusting for Z? Linear regression, multiple linear regression is Y Gaussian. That's a good question. Is Y Gaussian? And where I'm not willing to assume it's Gaussian for now. I mean, come on. I mean, in real life, what data is really normally distributed? Yeah. Okay, ANOVA, yeah, ignore the TMLE one, you're doing like, Joanne or linear regression, that kind of thing. Okay. But now that's the issue with the Gaussian outcome. Like what would you do if the outcome is not Gaussian and the residual variance is not constant? For me, or symbol transformation. Okay. Any other answers? What's our error? What the least square? Okay. I guess that's probably Fontaine regression. Okay. Box-Cox transformation. Okay. That's probably everything. Probably. Here's my own preference. Okay. I would run linear regression with sandwich or robust standard error because it's valid in large samples regardless of normality and homoscedasticity. So this approach is already semi-parametric, gives you valid inference in large samples as long as the linear mean model is correct. So you don't really, so it's kind of trapped. You don't need any normality or constant variance. And if you say we want to transform the variables, the issue is that would change the interpretation of the beta coefficients. And so that can change the scientific question we answer with the linear. And also we peak the data twice because you decide to do the transformation after you look at the data and see, oh, things are not normal, the variance is not constant. And that could also be a problem. Now, this one, so let's say we use linear regression, and then just think about what you might want to do if you find that the relationship is actually nonlinear. So in particular, if X and Y seems not linearly related, just think about that because you might there might be too many answers. So just think about that. And this again, my own preference. The ordinary linear regression estimates the true best linear model approximation to the true mean model. So let's say this model is actually the conditional mean of the outcome given the covariate X and Z is actually nonlinear. But then you run linear regression, then you're estimating the true best linear model approximation to this nonlinear function. And then if you use sandwich standard error, it still gives you valid inference for this best approximation. And this approach is fully non-parametric. Okay, so you don't need the mean model to hold, you don't need any normality, things like that. Then you automatically get valid inference for the true best linear model approximation. Now, are we happy with this interpretation? Maybe or may not. If you think that the linearity looks okay, I mean, if you only look at the overall trend, if it's not linear, even if it's non-linear, the linear approximation might give you the overall trend, but that might be okay. Then if you're not happy with that, then you might need to think more carefully about what that. Again, what you might want to do if you transform variables or if you add nonlinear terms in X, that can make the model difficult to interpret because basically you change the interpretation of the model. This is the last set of examples. So the only thing that we change is that the outcome is not continuous, it's binary, and we're in a cohort study. So how do you analyze the association between X and the outcome Y after adjusting for those?
No, it's not up yet. Oh, there it is.
Mononomial hospital, logistic regression. Regression.
What else?
Okay.
Geez, yeah. Oh, generally.
Probability. Okay.
Yeah, log, C log. TML.
Okay.
Yeah.
Anyone still? Any other answers?
Just log transfer.
Yeah.
Survival analysis. Okay. Binary regression. Okay. Here, okay.
Linear probability model.
Yeah. Okay, so here is it. So it seems like a lot of you said logistic regression. Just take a second and think about why you didn't choose any one of these. You could do Poisson regression. You could do law binomial regression. One person answered. At least there's one answer like this, and nobody answered linear regression. Nobody answered linear probability model. There's probability regression, C-law regression. Just think about why you didn't choose that. Is it because everyone uses logistic regression, or it's like that's the default approach I learned from my stat course? So you chose logistic regression. Okay. And also, if you want to use logistic regression, so what would you do if you really want to assess the relative risk and the outcome Y is not rare? Have that? Yeah, I have that. So what would you do?
Mark.
So basically, you cannot use odds ratio to approximate the relative risk because the outcome is not rare. Marginalization. What's the difference? What's on the link? Okay.
Imagine.
Okay.
Still just doing it.
It looks like it's not binomial, okay, Poisson regression, okay. So this is my own preference. So depending on the association of measure of interest, whether it's risk difference, relative risk, or odds ratio, I will run linear Poisson or logistic regression and use sandwich standard error when necessary. And this approach is also semi-parametric or non-parametric. I mean, it would be non-parametric if you don't want to assume the mean model is correct. Again, you're estimating the true best approximation to the true model. And okay, just one sentence. If you want to do log binomial model, it's efficient, but you might have trouble in computation because there are some computational issue. Okay, so far so good. Okay. I think that's all. If you want to do more, we can do that later. So just a bit more critique. I call these methods self-driving because we almost automatically set one of these popular standard off-the-shelf methods without much thinking. And self-driving approaches are convenient in many applications. I'm fine with that, but they have some limitations. So the first issue is that you subconsciously choose the scientific question based on the data type. So for example, usually we choose an analysis based on data type that's actually convenient for statisticians and answer a scientific question implied by that model. For example, if you have a continuous outcome, let's do linear regression, and that answers the difference in means. If we have binary outcome, let's do logistic regression, and that answers odds ratio. If we have right answer time to event outcome, like if you're doing a cohort study, some people just drop out, and you want to know, you want to analyze that kind of data, we often just do Cox regression, and then we answer hazard ratio. Then are we truly interested in these associations? Because they're kind of picked by statisticians or picked by those models. And another issue is that sometimes people would choose a method based on the data and then apply the method to the same data. Because, for example, we do variable selection, or we choose a transformation of variables, or we choose a more complicated parametric model so that the likelihood assumptions hold. So basically, we assume the likelihood is correctly specified. So for example, we log transform some outcomes or some variables. Or when you have a count outcome, you might do a negative binomial log linear model when the Poisson model doesn't fit. Or you choose a convenient non-parametric alternative when the parametric assumptions fail, like the rank-sum test. Now, but the validity of the hypothesis test and confidence intervals for almost all statistical methods relies on the method's assumptions like ID data, linearity, normality, things like that. And you need to choose the method before looking at the data. So if you choose your method after you're looking at the data, then we no longer have those guarantees, like like type 1 error rates or confidence interval coverage. And also these two issues, they can interplay with each other. So as we choose the method based on the data, we implicitly choose the scientific question based on the data. So if with different variables included in the model, we have different interpretations of the beta coefficients because you're basically adjusting for different covariates in different forms. And if you transform the variable, they also change the interpretation. For example, in a linear model, instead of doing the original outcome, you log transform it. Then the original question's difference in outcome means. Now it's the ratio of the geometric means of the outcome. Now is that? And also, if you switch to a non-parametric method, that also changes the question. Like if you switch from two-sample t-test to rank sum test, then the question originally was the difference in means, and now you're asking, I want to compare probability x less than y and probability x greater than y. Now, do we really want to change the scientific question based on the data we observe? And you've probably all seen this kind of flowcharts in some kind of stat books. They just say what kind of data you have, it's continuous, this kind of how to do analysis. I saw one when I was proctoring an epi exam. I hope they didn't use it. And you can see this kind of parametric assumptions. Is it satisfied? Yes. And if no, we try a transformation. If it's still not normal, we do a Burke-Hodgson rank-sum test. If it's normal, then we do a t-test. I mean, it's like it basically has all kinds of issues we just discussed. Okay, so because of these issues, we might want to aim for full control of the estimate before looking at the data, and a robust statistical method that relies on minimal assumptions on the data generating distribution so that we minimize the chance of assumption violation after looking at the data. Okay, does that make sense? Okay, and this is basic. Okay, I'll just say a few more words like why do we have those kind of issues with self-driving methods? So conventionally, we try to come up with a mathematically simple model for the data, and then use the model parameters to answer the scientific questions. Like you fit a linear model, use that beta as your effect. Now we have one model for at least two tasks. So you want to model the truth. You want the model to contain the true data generating distribution, and it has to be useful, so it has to be interpretable, because otherwise you won't be basically you won't be able to use it. And hopefully it's easier to compute, but I mean different statisticians have different standard criteria for computation. Now, an interpretable model might be more likely to be false and vice versa, because nature need not be parsimonious regarding to our question. So that means all models, I mean, it might be parsimonious, like if you go down to the very low level quantum physics, that might be interpretable to some people, but then you cannot derive what patients behave based on quantum physics. So all models are wrong, but some models are useful if they can achieve a balance among those tasks. But then there might not be a perfect balance. And also the right balance can be subjective. I think I should add a spline term, and maybe you think, I think the linear term is fine. So, and also the domain experts, they might lose control of the estimate when statisticians choose the right balance. So it's just like we pick hazard ratio for you when you have right sensor data. And how do we solve this issue? So this is a potential solution in our area. I'll call it manual driving instead of self-driving. So we decouple those tasks. So we change the norm and specify a statistical problem with two components before looking at the data. So the first one is the true model. So we assume that the true data distribution falls in a model. So falls in some set of distributions. And ideally, this model is specified based on prior knowledge and assumptions only. So usually it's very rich, non-parametric, so it's very hard to interpret this model. Now, this is rich enough to contain the truth, but we cannot interpret this model. So we need a second component, which is an interpretable estimate. So we specify a map inside that you put in any distribution in this model, in this set of distributions, and it spits out a real number such that it answers the scientific question of interest about that distribution P. And this mapping, in our area, we call it a parameter. So parameter, so basically you have one population. For any population, you tell me how you want to summarize that population. And that's the mapping, what this mapping does. Does that make sense? Okay, so I'll give you some examples, some very simple examples. I look at the population mean. The true distribution can be very complicated, but all I want to know is the mean. So I have this parameter. So you give me a distribution P, I summarize it by looking at its mean. So, least squares, it's a bit more complicated. So under the distribution P, I look at all linear models, X transpose beta, and look for the beta such that minimizes the mean squared error, where the mean is taken under P. So under this under the population, what's the linear model that gives me the smallest squared error prediction error measured by the squared error? And you can show that it equals this linear model is also this linear model. So it's the true best linear approximation to the true model. So for this part, this is the true model. This is the best linear approximation. And this is the linear model, and we're looking for the linear model that approximates the true model best. Okay. And then we study how to estimate this parameter well under assumptions encoded in the model, in the set is in this model M. Does that make sense? And this approach is particularly suitable for inferential or confirmatory analysis. So if you're very clear about what you want to estimate, this will be ideal. So this framework, so that's why it's hard for me to explain what I'm doing, because this is so widely applicable. So you give me, basically I only need those two components, right? You give me a set of distributions and you tell me how you want to summarize it with this parameter, and I tell you how to estimate this parameter. And this has been widely used in causal inference to estimate average treatment effects, heterogeneous average treatment effects, optimal and individualized treatment rules, etc. And we're extending this application to other areas like right sensor data, working on it, machine learning, which is my job talk, and patient-reported outcomes. I'm also working on that. And disparity, we once wanted to work on that. And capture recapture, and potentially more. That's where, I don't know the limits of what we can do. So basically, this is the core of my research is mostly about how to translate your scientific question into the model M and the parameter psi. So basically, how you want to summarize the population, and then how to estimate this parameter in a robust and efficient way. So efficient basically means it gives you the smallest variance in large samples. So item one can be very challenging, and it may vary case by case, because we need to translate a question in everyday language into rigorous math. If you think about it, it took more than 200 years for mathematicians to translate probability into rigorous math. And it takes forever to translate causation into rigorous math. And also, we might need additional assumptions for this translation, particularly in causal inference. So we often need some potentially untestable causal assumptions, and we call them identifying assumptions, so that the causal estimate equals the parameter of the observed data distribution. I'm mostly talking about the potential outcome framework. So there's a counterfactual world, and what we only have data to from the observed data world. So now we can do the best in terms of the observed data, but now you need something called identifying assumptions to connect those two. And I'll give you an example later. And for item 2, it's more technical, tedious, and standard. I often rely on something called semi-parametric efficiency theory. So that's for Don, that's what I taught last spring in the independence work study course. So a bit of it was quite some torture for students. Okay, so for domain expert collaborators, here's what I need from you. You need to formulate the scientific question even vaguely, and then we can discuss how to translate it into a parameter. I know it's very hard to say what exactly you want. You probably know what you don't want, and then we can try to discuss and carve it out. So this requires careful thinking, particularly under weak assumptions. For example, what do we mean by overall trend if the relationship between X and Y is nonlinear, right? If it's linear, we know what exactly what overall trend means. It's just the correlation or the beta coefficient in the linear model. But now, if it's nonlinear, what do we mean by overall trend? Or do we care overall trend at all? So, and also, you might want to be bold and open-minded. Existing methods might not address your original research question, but a shifted one. It's just like how a Cox regression answers hazard ratio, but typically we don't care hazard ratio because hazard is very hard to interpret. And existing methods might give an unnecessary conclusion for your original question under unrealistically strong assumptions that are necessary for the methods. So instead of your original question, they try to answer a stronger question. And to answer that stronger question, I need stronger assumptions. So that's how things work. And maybe it turns out you don't need those strong assumptions to answer original questions. And this thought experiment might be helpful. So if you can collect infinite amount of data using the same study design, then what is the number you want to calculate from the true distribution so that you can answer your scientific question? So you know the true distribution exactly, and you don't need to model that. So you don't need to model conditional mean with a linear model or a logistic regression model. You know that exactly, even though it's complicated. And you also inherit the limitations from the study design. So you can't say, I'm doing a case control study. Now I have infinite cost. I can do a randomized trial. But under this framework, you still have to do a case control study, but it's just that you have infinite amount of cases and controls. And this is what I would give. I would give a solution tailored towards your question. So it's an interpretable parameter with transparent identifying assumptions based on your prior knowledge. I will clearly state the parameter so that it addresses your question along with the identifying assumptions, and try my best to make the assumptions interpretable and consistent with your prior knowledge. And also a robust and or efficient estimator. I can give you an estimator with theoretical guarantees like it's efficient in large samples, it gives you valid test or confidence interval in large samples, and maybe multiple robustness. I'll give you an example of what this means. And clearly state and hope the assumptions, hopefully they're interpretable, but they tend to be more technical than the identifying assumptions. Okay, so far, any questions so far? Okay, I'll just give you one example that's not so trivial, just in causal inference. It's not I didn't develop those results. I'm just using, they were developed before I was a PhD student, but just using those for as an illustration. So let's say, you have a population, for every person in the population, they have some covariate X, like including age, sex, race, things like that. And a binary treatment, for example, on healthy versus healthy diet. I know this is not well defined, but let's say you can categorize that, diet into those two categories. And two potential outcomes, like whether you have metabolic syndrome, whether you have diabetes, or maybe BMI. So Y bracket 1 is the outcome that would occur if the individual were to receive treatment 1, and Y0 is the outcome that would occur if the individual were to receive treatment 0. And let's say we want to learn about the mean counterfactual outcome. So the expectation of Y1, so that means the population mean outcome that would occur if we were to have everyone take treatment 1. And the other one, I mean, Y0, the other counterfactual mean is similar. You just switch the label of the treatment. And then you can take the difference. That's what we call the average treatment effect. So far, so good. So I'll focus on EY1 for now. Now, what do we observe? We take a random sample from the population, and we observe their covariate, their binary treatment, and their factual outcome, because we cannot observe both potential outcomes, because you cannot have them both take treatment 1 and take treatment 0. So the true observable data distribution is a distribution over XAY, so it's what we can observe. Then, without any additional knowledge or assumption on the true distribution, I'll assume a non-parametric model. So we're not going to make linear assumptions, and we're not going to model the data. Say it's non-parametric. Then what is the parameter that addresses the mean potential outcome? So we need some additional assumptions to connect the counterfactual world, where you have the potential outcomes, and the factual world. And there are several sets of identifying assumptions. I'll just focus on the most common one. So positivity, so probability that the treatment A equals 1 given X is in 0 and 1. So that means so in the population, you can group people based on their covariate value. Then within each stratum, the probability of receiving both treatment is positive. So you have some chance to receive both treatment. And no one measure confounding, which is written in this form. So the potential outcome is independent of the treatment given X. That means within each subgroup with the same covariate value, people are like randomized into the two treatment arms, or at least people taking the two treatments, they have similar potential outcomes. So you can use the people with unhealthy diet to extrapolate the potential outcome for people with healthy diet and vice versa. And under those assumptions, you can show that this is the parameter we're going to do. And so what does this expression mean? So the inner expectation here, it means basically for every individual, we're going to predict their outcome if treatment 1 were received based on their covariate X. Okay, so, and then for the outer expectation, so this is a function of X. This is a function that only depends on X. And then the outer expectation is over X. So it's basically expectation of Fx. So that means we average the predicted values over the population. So what this is doing is that in the population, we predict their outcome for everyone, we predict their outcome if they were to receive treatment 1, and then average predictions, and that's the average potential outcome. Does that make sense? And so far we have made no parametric assumptions, but then this parameter is still interpretable. Now the estimator, I won't show you what that estimator looks like, but after some tedious derivation, you can show that the augmented inverse probability weighted estimator is efficient and robust. I'm not showing you what this estimator looks like. You can Google. There's a Google Wikipedia page with the expression. So it involves estimating two nuisance functions. One is the outcome model, so it's basically the model that's used to predict the outcome given covariance. If you were to receive treatment one. And the other one is the propensity score model, so the probability that you receive treatment given your covariance. So within a stratum defined by the covariant value, what's the probability you receive treatment one? And you can show that this estimator is asymptotically normal and efficient. So that means in large samples, it's approximately normally distributed with the smallest variance possible. If both those two models are estimated well. So now it's a very high level condition. It's just saying they're estimated well. Now that means you can use machine learning to estimate it if you don't want to make any parametric assumptions. If you don't want to use linear model, if you don't want to use generalized linear model, if you think those are potentially misspecified, you can use machine learning, like neural networks or random forests. And you can still use parametric models, but now we view those parametric models as approximations to the true model. We're not assuming they're correctly specified. And it's also doubly robust. So the estimator is close to the truth if one of those two models is estimated well, without knowing which one of them is estimated well. Okay. So that's what earlier I said multiple robustness. That's basically a more general version of double robustness. Okay, so any questions? Okay, I'll just wrap up. So self-driving methods can be convenient. But sometimes we might want to drive manually to have finer controls and safer analysis. And I develop methods for manual driving. And to initiate, I need a meaningful scientific question to be translated into a parameter. And I can develop efficient and robust estimators tailored towards your question. And be open-minded and bold when asking the scientific question. And as Jamie Robbins said, it's not so hard to think outside the box if you're never in it. So, I mean, I'm new to your area, so I'm never in those boxes. Well, thank you.
Could you tell your collaborators if the identifying assumptions are not satisfied?
Yeah.
You can do it. I mean, you have to do something outside sensitivity analysis. I mean, some people do bounds, but then there are also, I mean, I'm talking about causal inference in particular. They do bounds, but then the bounds also have some issue. I mean, they can be, the bounds, you can have trouble with inference for bounds because of some statistical issue or mathematical issue with it. And they also, sometimes they do auto bounds, so they automatically come up with a bound for the treatment effect you're interested in. And now the issue is that inference is also difficult, and they often assume the covariates are discrete. So I don't think there's any perfect solution. I mean, sensitivity analysis can also be problematic because there's basically infinitely many ways you mess up your identifying assumptions. And typically they just look at the deviation in one or a few directions. And it's like maybe in those directions your conclusion is robust, but in other directions it's not so robust.
So I'm curious, and I should say for folks, I've had the benefit of being able to collaborate with you, and I can definitely say that I very much appreciate you being able to meet me where I'm at when we're talking about all of these assumptions and how we might navigate them. So, you know, I feel thankful to collaborate with you in those ways. My question is it's kind of application focused, probably not surprisingly. Are you aware of any major like epidemiologic finding or something like that where the conclusions we've drawn or have believed to be true about a certain topic area have changed following the adoption of methods that don't make these stringent assumptions.
And being trained as a methodologist, I didn't focus on this kind of things. But I think if I remember correctly, Jamie Robbins gave an example he had. It was a clinical trial, but then people would just drop out during after the treatment initiation. And then they want to compare like if you stick on the treatment group versus not stick on the treatment group, those two groups. And if I remember correctly, a traditional method and methods like this will give quite different conclusions.
It's like one of the examples is the hormone replacement therapy example for women's health studies, right? Like, also, I think if you look at this free online course by Miguel Bernal, there are several examples, like the smoking effect on Alzheimer, I think it's dementia, like, right? Yeah, and then things like screening for cervical cancer related.
My question might be in the weeds a bit, and maybe not related enough to what you're talking about, but you kept mentioning several times about transforming the data being problematic, because now you're changing the question. But if you deal with a lot of biomarkers, almost all of them basically require log transformation. Like nobody does analyses of these various cytokine levels and things like that without transforming them, right? Do you think about that as really changing the question? I mean, is it, or did you have other things in mind when you were talking about that? I mean, I get that they change what that coefficient means, but you can't really look at them without transforming them.
It's like if you decide to transform it before you look at the data and you know exactly what you're doing with the
Oh, you mean if I haven't looked at the distribution at all?
Right. I was mostly talking about if I decide to transform the data because the data doesn't look normal. Now that's problematic. If you're happy with the transformation, I mean, log transformation, it probably corresponds to some biological mechanism. If I might be wrong on this, but I think there are some simple models like from differential equations, and the solution is like exponentially something that then you take the log. That makes perfect sense, and that corresponds to you. That it's exactly what you want to do. So that's fine.
I think I saw this paper like saying, in the lab, if you're training as an experimental scientist, and you have all these biomarkers, it's just straightforward, just always transformation and then do the analysis, right? But then if you're a population science epidemiology, you don't do that. And I think I just saw a paper talking about both are needed, like both, they have different sort of purpose, I guess, like, but it's like we're in different boxes, right? We are training our discipline and we don't really talk to each other. So we should probably talk to each other more.
Thank you for your talk. It was very interesting. I could see what you were thinking about it being inside the box or outside the box. Can you back up 2 slides so I could ask a question? I think it's 2. Yeah, but no, it's the one just after that. There you go. So in the last 2 bullets, what are your personal criteria for evaluating whether one or both are estimated well?
So so first, I mean, in terms of theory, it's an assumption. So it's like it boils down to how do you what either you can show the assumption holds. Basically, that means under some other assumption, or you basically think about whether you believe the assumption holds. And what I can say is that we have shown that under some very weak, I shouldn't say very weak, but under some I mean, arguably mild smoothness assumptions. I mean, things like what is it? Under that kind of assumptions, if you use neural network, then you can guarantee it works well, at least in large samples. Of course, you don't want to just blindly put in neural networks. You want to use some other, but you might want to use a linear regression as well, just because linear regression actually performs pretty well. I mean, in terms of approximating truth, it's pretty well in many examples. Then you can ensemble them. That's what we're doing in an algorithm called superlearner. So where you can ensemble the machine learning methods or parametric methods. And as long as one of them estimates the true model well, then the overall output, the ensemble learner will also learn things well. So,
Do you have an approach that uses tuning either in either direction, either tuning better to make it better or tuning badly to mistune and see if your conclusions, if your inferences differ across the tuning parameters?
yeah, we didn't do that kind of simulation, but I think you can make I mean, if you put in a very bad fit, so when you say two things, I'm thinking how my brain is runs very slowly when I talk to people. Yeah, okay, so if in the simulations, if you put in a very bad use those two model estimators, then you can almost guarantee that your estimator will be bad. And I mean, you can, and there are a lot of simulations where you show that if you do one of them very well, the other one is completely wrong, then your estimator is still close to the truth. And we have shown that in a lot of simulations. Does that answer your question?
Yeah, thank you. Yeah, I think so. I mean, it would be interesting to know in another talk how you think about making how you think about departing from the criterion of estimating well, so that it isn't just a belief or an assumption that you bring to the study, but it's something that you actually can examine and see how bad would your approach have to be in order for you not to get the answer that you're getting with what you believe to be the best answer. You see what I mean? It's just basically, in a way, it's kind of a sensitivity analysis to say how far off could I be if I'm wrong about my model, if my approach being estimating well.
I see. Yeah, that would be an interesting approach. Yes. And I mean, related to that, Jamie Robbins had a paper. I think more than one paper is about this estimating well. So they basically given you the data and given the models, and they try to come up with ways to falsify this assumption. You cannot do that exactly. I mean, because this is when estimating well, you cannot do exactly because it's about the truth, and you never know the truth. You can never strictly falsify it, but you can falsify it. You can falsify the argument to show it estimates well. So the argument is like this. When we say both are estimated well, what we have is typically like something like this. So the product of those two. Yeah, we typically do things like this is bounded by the difference, the product of the error for each. That's how we typically do it. And he can falsify whether the product is too large compared to compared to the normal part. Now, the issue is that even if you falsify this, you still cannot falsify what's smaller, whether that's small enough. But at least you falsify the argument.
Thank you.
So David, you have a question. So so when the two models are parameter, typically, people tend to use some bootstrapping, for the standard error. So in the setting where I have a purely non-parameter or even a machine learning approximation, so would the bootstrap still work or not?
The tradition is not to bootstrap because you can show exactly, sorry. You can show exactly I'll call your estimator psi hat. You can show exactly, this it's approximated by a sample mean of some function of your data. And now this function involves some truth, but then you can estimate this function. So as long as you can consistently estimate this function, you can get a consistent.
The inference function?
Yes, you get it, yeah. If you want to bootstrap, there are issues if you do a full non-parametric bootstrap. The usual bootstrap usually doesn't work if you're doing machine learning with cross-validation. I mean, you choose the parameter based on cross-validation, but you can just bootstrap xi. You keep your nuisance functions estimator the same. And basically, you're just bootstrapping this part. You're bootstrapping the empirical distribution part. You don't bootstrap the estimators of those functions. Then you're still good.
I think there's a paper called targeted bootstrap.
Oh, yeah.
I'm not talking about that. I'm talking about a more recent one by Ted Wesley. There's an archive preprint. Because the target bootstrap, I think there are some issues because you also need to generate data from the estimators of those things. And if your outcome is not binary, then the outcome model itself doesn't give you the full distribution of the outcome. You cannot generate data from the outcome.